Good afternoon, everybody. Let's go ahead and get this party rolling. This week we're going to be talking about artificial intelligence and machine learning, which is a really, really large and broad topic that is impossible to completely cover everything in even one class. I mean, there's tons of classes out there and tons of courses devoted to one specific topic in there. So we're going to give a higher level overview, an example of how it's used and various topics with that today and on Thursday. So let's go ahead and dive right in. So artificial intelligence and machine learning. So the first question we have to ask ourselves is, what is artificial intelligence? Well, an easy way to describe it is intelligence exhibited by machines. And this is kind of a broad generalization of it, but that's the easiest way to rationalize it. So it's the ability of machines to react to their environment, take actions that minimize or maximize a problem, identify objects, phrases, etc. I specifically mentioned minimize or maximize a problem. A lot of machine learning is having a whole bunch of data and figuring out what the largest number is in a section or what the smallest number is. Or you have a function and figuring out what values make that function the largest value. It's a lot of math that sometimes you have to worry about, sometimes you don't have to worry about, but it's still there. So minimizing or maximizing a problem. It's very much like when you're, say, playing a board game and you have multiple ways to um, complete a action, but there's one path which may be more optimal than others. That's a maximum or that's a min-max problem where you're trying to find the maximum value from the path that you're taking. Uh, so artificial intelligence research and all this machine learning and everything started in about the 1950s. It experienced bursts of growth ever since, up until the 1980s. So during this time, it was, I guess, initially science fiction. They started to come up with ideas for robots taking over the world or robots helping you and everything. And so they started to research this. And as computers became more and more popular, even in the research areas back then, they started to focus more and more on creating robots because, well, everybody wanted to have their own robot butler. Well, they started to run into some problems with this, and the money which was getting funneled into research um, started to get funneled elsewhere. And so, about the 1980s is when a lot of the companies which were funding this, they started to focus elsewhere, things which were making them more money. And that was known as the AI winter or artificial intelligence winter. When funding dried up, people weren't really able to get jobs in it. Some people even thought that it was never going to advance further than what it was. Back in the 1950s, people were predicting that everybody would have their own robot by the 1970s. Well, that obviously hasn't happened yet, and even now people are predicting that we'll have robots within 20 years. I'm predicting that we'll have robots sometime. I don't know exactly when. I mean, I hope it's within my lifetime, but it may not be until the 2100s or even later. It just depends. Currently, AI is widely used in almost all aspects of life and is, at this current point in time, very, very well funded. If you have experience developing machine learning and artificial intelligence systems, and you can demonstrate that, you can easily get a six-figure job working for any of the large companies out there, like Facebook, Amazon, Apple, Google, Netflix, any of them. There's also other companies like Tesla, OpenAI, um, Uber, any of those. It just depends upon what you focus in, but you can easily get a job making six figures without a problem. There's even people who develop their own AI system and then they turn around and sell it to one of the large companies for many, many times what it costs them to develop it. So it's really, really well funded because everybody wants to make the next step to having an AI system that they can sell to other people. So that leads us on to machine learning. So the topic of this is artificial intelligence and machine learning. So what is machine learning? Well, it's kind of a subset of artificial intelligence, and artificial intelligence is a subset of machine learning, so they're kind of sets of each other. But machine learning is more of the study of algorithms and statistical models for computers to perform a specific task without explicit instructions. It's a way to develop a system to figure out what's going on. Not necessarily have a robot, but to have a computer analyze a whole bunch of data and decide what that data actually means. Or even if you feed it a whole bunch of data, then the machine learning algorithm may decide how to classify that or how to act on it, but it may not actually act on it. It may just give out a bunch of results on saying, this is a most likely outcome given this data. It relies on patterns and inference. It's seen as a subset of artificial intelligence. It uses statistics to make predictions or categorize information based on past training models. So this is one of the big things that I've actually been working on with there's in the class machine learning for trading. It's about taking a whole bunch of market data and a whole bunch of statistics related to it, toss it into a big bucket, and let the computer churn around in there and then spit out an answer, such as if you have stock XYZ and you have all these statistics for the stock for the last year, what is the most likely outcome for that stock tomorrow? Or is it going to go up? Is it going to go down? It's going to stay the same. What should you do with your money? There's a huge industry just in machine learning in the financial sector. There's also a huge industry in machine learning in the entertainment industry. What do people watch? Why do they watch certain shows and certain movies? Or in commerce and industries such as shopping. Why do people go to these stores? Why do people buy things? So machine learning is basically taking all of this data and then figuring out what to do with it. So the history of all of this. So in 1950, English mathematician Alan Turing. We should all remember the name Alan Turing. If you don't, well, you should definitely go look it back up because he was an important figure in computer science. He was the one that created the Turing test, which is what we're actually going to be talking about. He wrote the paper called Computing Machinery and Intelligence that asked the question, can machines think? Or can you get machines to a state to where they can think? So he devised this test, which was known as the Turing test, to basically see if a machine could exhibit intelligent behavior equivalent to or indistinguishable from that of a human. And I mentioned this, well, back in the first week of the semester, but just as a quick review, the idea is you have three rooms and all the rooms are separated. You have a judge in one room, and that judge has two inputs, one from room A and one from room B. And the judge doesn't know which is in room A and which is in room B. There could be a human in room A and a human in room A and computer in room B, or a computer in room A and a human in room B. The judge doesn't know. The judge's goal is to determine which room has a human and which room has a computer. And they do this by asking a number of questions and seeing what the answers are. And the goal of the Turing test is to create a computer system that produces answers to any of these questions that can successfully fool the judge into believing that the computer is a human. And it's one of the key topics in artificial intelligence is how can you create a system which can fool other humans? And we'll see examples of some systems which kind of close, but not quite, and some discussion as to why they get close and why they fail and what can be done and that sort of stuff. So that's the Turing test. In 1956, AI research was born and named at Dartmouth College during the Dartmouth Conference. The professors and students created computers that were learning checkers, solving word problems in algebra, proving logical theorems, and speaking English. So before that, it didn't really have the name artificial intelligence up until 1956, and that's when it became named artificial intelligence or AI research. So after that, funding started pouring in. Within years, labs opened up around the world. Predictions of computers doing the same work as people in 20 years were made. So if we think that 1956, people were saying that by 1976, computers were going to be doing the exact same things that we were doing, which, I mean, looking back, we now know that that's not the case. But if you were back in the 1950s, suddenly seeing these computers playing checkers seemed magical at the time, and people had lofty visions of what was going to happen. 1974, funding dried up and AI research was reduced until 1980s. There was still some research going on, but it was vastly reduced uh, until 1987 when Lisp machines became less popular. Lisp, that is the programming language which uses a lot of parentheses. That's the kind of the thing that a lot of people remember it. But Lisp was actually created for artificial intelligence research. And there's still a lot of systems which use Lisp. It's not used as much, but the way it was designed was specifically for artificial intelligence. And so a lot of the concepts are easily or more easily implementable in Lisp. Uh, then in late 1990s, AI started to get used in logistics, data mining, medical diagnostics, other areas, which opened up huge new areas of AI research. Um, then let's see, 1997, Deep Blue. Again, if we were in class, I'd ask, has anybody heard of Deep Blue? And there might be a couple of people raising their hands. This was a really, really big thing back in the day. It was the first computer chess playing system that was able to beat the reigning world chess champion Garry Kasparov in May 11th, 1997. Uh, I vaguely remember this. I think it was Garry Kasparov stated that no computer would ever be able to beat him, and I think Deep Blue managed to prove him wrong. Deep Blue was created by IBM. They were the creators of Deep Blue, and it was the first computer chess playing system that ended up beating him. It went on, I think it played against several other chess grandmasters and managed to win as well before I think it got retired. In 2007, checkers was solved. So, what do I mean by solve? Well, there's several variations of this, but a solved game, and I'm looking at this from Wikipedia, it is a game whose outcome can be correctly predicted from any position, assuming that both players play perfectly. So checkers, it's played on the same size as the chessboard, which has 64 squares. It's an 8 by 8 grid. And you have either red or black, and the goal is to capture all the opponent's pieces. So given all that, there are 5 times 10 to the 20th possibilities, which is a fairly big number. Um, so you can think of it as you want to completely drain the Pacific Ocean for some reason. Maybe you hate the ocean and you really want to drain it. And so you have one tiny cup. And this isn't a regular ounce size cup or even a 64-ounce big gulp that you can get from the gas station. This is a little cup that you get from the dentist office, which if you want to actually drink any water, you have to fill it up 5,000 times in order to get one glass of water or one equivalent glass. But anyway, you take that cup, fill it up, and you dump it out, and then you do it again, and you keep doing that. And the C is the number of possibilities, or 5 times 10 to the 20th, for every cup. That's the number of times that you have to drain the Pacific Ocean. That's how big checkers is in a computing sense. And it became the first solved game. First, not the first solved game, but it became solved in 2007, which means that a computer, if it plays perfectly, and assuming the other player plays perfectly, it knows at the very beginning, within the first move, who's going to win and how to win. And at any state, if you give it a state of a board, a computer can tell you exactly which moves to take that will win. And so 2007 became the first solved game. There have been several other solved games. Tic-tac-toe is one of the easiest solved games. It's a 3 by 3 grid where you can do um, X's or O's, and it's guaranteed that if both players play optimally, then the game will end in a tie. If and depending upon who goes first, you can force a tie, or you can force, given it, you can determine whether it's a win, loss, or draw. Connect Four, that game where two people play and you have either a black or a red disc and you drop it down and you try to get four in a row. That is also known as a solved game. So checkers joined that realm in 2007. Um, so computers are able to solve checkers, but there are other games which are much, much bigger than checkers. So I'll get to that in a minute. So 2011 Jeopardy quiz show between IBM's Watson, IBM also made Deep Blue, and two champions were held where Watson won easily. It was able to beat two other human players fairly easily, from what I remember. I think it went on to again, and I think it won again. I'm not 100% certain, but I remember watching a little bit of the Watson Jeopardy games, and it was rather interesting. And then in March 2016, AlphaGo. So again, this would be a time in class when I would say, "Does anybody know what Go is?" So we'll go here, and we'll go here, and Go game. So Uh, yeah, that'll work. So this is a ancient game from China. I wish this image was a bit bigger. I think I could click on that. And yeah, Wikipedia. This is a game from China, and it's a strategy game. You are either the white player or the black player. And what you do is you take turns laying stones down on this board. And this is I think it's a 19 by 19 grid, and you place them on the dots in between there. If you have all the stones surrounded by another one, so like in this case, all the black stones surround these white stones here, these white stones are captured or dead. They aren't necessarily captured, they're dead. They can't do anything. There's no move which will actually capture it. And the goal is to get it to a state to where you control the majority of the territory, and your opponent does not. And so if you think of a checkers board or chess board, which is a 8 by 8 grid, so there's 64 possible squares. A Go board, on the other hand, is a 19 by 19 grid, which that is, and I'm doing quick math in my head because I can do it ahead, 361 possible locations. Now, to add to the complexity, in chess, each piece has set movement rules. Pawn can move forward one or two, attack diagonally, whereas bishop can move only diagonally any number of spaces, etc., etc. Checkers, each piece can only move diagonally forward, or it can jump over a piece, or if it's a king, it can move diagonally in either direction. So the number of possible moves are rather limited. Whereas in Go, there's no limitations. If you want to place a stone here, the only limitation is you cannot place a stone where it would already be dead. But you can place a stone here, or you can place a stone there, or you can place a stone up there. The The only limitation is it cannot already have a stone there, and it cannot be a spot that would already be that would make the stone captured right away. So even though there's 361 possible locations, the number of possible moves is exponentially larger than that. And so a computer is not able to start from current slide. A computer is not able to determine just from the board what the optimal move is, just because there's so many possible options. And so this was a big problem for machine learning and artificial intelligence is how does a computer actually solve this? And so the traditional methods of, okay, we're just going to throw a whole bunch of possible moves at a computer or a whole bunch of games at the computer and just let a computer build a tree and then walk down that tree to determine which move it should actually take doesn't really work. So what the groups at AlphaGo did, and this is a group which is part of Google, is they took this idea of, well, we can't build a tree to calculate all of this and know at any particular state what the correct move is. So instead, we're going to build two systems. And each system is going to have the rules of Go implemented in them, and they're going to play against each other. And then they're going to record that. Then they're going to do it again and again and again and again, et cetera, et cetera. And it will play against itself or play against each other millions of times. Each time it records every game to determine what strategy got it to that particular state. And it did this millions of times. And eventually they took the system that they built from that and they stored it. And then they took their computer and played it against the reigning Go champion Lee Sedol back in 2016. And Lee Sedol, he is or was the world champion at Go, which means that he was the best player in the world at playing this game. And he played against AlphaGo, and AlphaGo won 4 out of 5 games, which at the time was mind blowing because it's such a complex game for humans to play. It was seen as an insurmountable game for a computer to be able to play against a world champion. And I watched some of the commentary on this, and they were analyzing it, and it was rather interesting to see because they it's one of these things that's you think that analyzing a board game playing match can be boring, but the people that talk about it, they keep it rather interesting. But as they were doing this, AlphaGo made a move, and the commentators were like, "Oh, that's a mistake. That is a move that um, opens up all sorts of avenue for Lee Sedol to attack AlphaGo and gain an advantage." 20 moves later, AlphaGo made another move that the commentators realized was in response to the first move 20 moves earlier that it made. And they realized that the move that AlphaGo made 20 moves earlier was not a mistake, and it was setting up a move that it made 20 moves later. Which, if you think about that, is kind of fascinating that a computer can set up a state that then it pays attention to what's going on, and 20 moves later, it makes another move in response to what it had done initially. And the initial move that the commentators said was a mistake, they now realize was actually a very subtle action that no human, and these are the words that they stated, no human would have made because the strategy that AlphaGo implemented was not a strategy that a human would have come up with, at least not at that current point in time. And because it made that strategy, I believe that it was one of the 4 games that AlphaGo won. It was able to capture the win because it was making moves that a player who is a world champion in a board game and knows everything there is that any current living human knows about would not have foreseen because it's not something that they would have made. And that's kind of the power of machine learning and artificial intelligence is the computer able to take actions that normal people would not be able to see because they wouldn't picture that as actually having a benefit. But a computer can see certain trends and patterns in the numbers and in the data, and make a move that 20 moves down the road suddenly pays dividends. So AlphaGo, I encourage you to go out and search on AlphaGo and read up about it because it's really, really fascinating how they managed to build the system and get it all to work. In slightly more modern times, which, okay, 2016 is only 4 years ago, which is really modern, but in the world of artificial intelligence, that's ancient, ancient history. In more modern times, the or the creators of League of Legends and StarCraft 2. League of Legends, I don't remember who manufactures that or who maintains that, but in StarCraft 2, Blizzard. StarCraft 2 is a real-time strategy game where at any point in time there's any one of 1,000 different things that you can do. It's kind of like Go to where you can place a stone on any spot on the board, but it's kind of open-ended that way. Where StarCraft 2, you can decide to click on one location or um, build a new unit or queue up a unit. And there's literally thousands of options at every second of the game as to what you can do. And so Blizzard created an API. So what is an API? Well, it's an application programming interface. It's how you can write a program to interact with another program without actually having to know what that other program does. The other program, in this case StarCraft 2, presents a number of interfaces. And those interfaces, when let's say I write a program, I can tell it to send that instruction to the game, and it does that without actually knowing how that game is written. And so Blizzard has opened this up to where people can write software and write software to try to improve artificial intelligence and to play the game. And the initial software programs or initial artificial intelligence systems which were created for this weren't that good. But over the years, they have played they played their system against world champion StarCraft 2 players, and there's been a number of instances where the world champion players have lost to a computer system because the computer is doing things and has had the experience of learning from several other world champion players, and it's doing actions that the professional player is not able to predict. And it's actually starting to become more and more successful against them. So in more modern times, computer games are starting to become a avenue for artificial intelligence research. So what is the motivations behind this? Computers are better suited for mechanical computations using fixed rules. So if you remember, again, back from the very first week of class, the brains of a computer or the CPU, they have an ALU or algebra or arithmetic logic unit or algebraic logic unit. I can't remember if it's one of those A's. But this is the uh, piece in the CPU which is able to add, subtract, multiply numbers really, really quickly. And it's really, really, really good at doing that. Um, Computers, they're also really good at monotonous tasks. I mean, if you had to assemble 5,000 hats for some reason, you start sitting there and you start doing it and you get really bored really quick. Whereas computers, they don't get bored. They just keep cranking along and keep doing it. Another motivation is enhancing our current understanding and improving upon what we know or do not know. Again, in the examples of like AlphaGo, where AlphaGo made a move that a human would not have made, that's enhancing our understanding of how it's currently working and how it's supposed to be working. It also allows us to understand our thoughts and reasoning, to try to figure out how we can make a computer think like us, makes us understand how we think more, increasing knowledge and abilities in the world. Again, trying to make things better, make the world a better place. I mean, this is just a small subset of motivations, but there's a lot of motivation behind getting artificial intelligence and machine learning to a viable current state. So now we move on to some limitations. And again, I kind of wish that we had class and I could stand in front of you and have you um, give me some feedback. And if you wanted to type something with any of your own limitations, feel free. But one of the limitations is, when will they become intelligent? So intelligence is a hard thing to measure. And that's actually kind of the next question, is what defines intelligence? But when will they become intelligent? Um, is it when they can make their own decisions without a human providing the input? Is it when they can decide between A or B without knowing what A or B is ahead of time? Um, and then it brings up the what defines intelligence. I mean, we'll know that humans are intelligent. Well, some humans are intelligent, some are more intelligent than others, some less, but that's we all exhibit some form of intelligence. That asks the question of, do animals exhibit intelligence? Uh, you'll have some people say that animals are not intelligent, and some that say animals are intelligent. They they exhibit different levels of intelligence. I mean, my animals, my pets, I think they're intelligent half the time. The other half of the time, they kind of ignore me, so they aren't as intelligent. But maybe that's their own intelligence. So, what exactly defines intelligence? And this is kind of an open discussion point of, how do you actually define something as intelligent? Is it the ability to put two things together and know what those two things are? What about the ability to create artwork or create some abstract concept? Or what about the ability to explore new topics that they had no interest in before or no knowledge of before? Um, there's one of the things like animals getting or exhibiting intelligence, such as crows and birds starting to use rudimentary tools out in the wild, or primates using various tools and stuff like that in the wild. That's some form of intelligence. But how do we actually classify what intelligence is? Um, Another limitation is it requires supervision. And so current artificial intelligence systems are rather limited in what they can do. Uh, and when you have an artificial intelligence system, you can't just release it upon the world, because it's just going to, in the best case, just kind of stop working. In the worst case, well, we've all seen Terminator or iRobot, which I'm not saying the crappy movie iRobot. I'm talking about the books iRobot, but neither here nor there. Or Battlestar Galactica, when the Cylons started to take over the universe. Uh, we Science fiction has talked a lot about what happens when artificial intelligence rises up against the human creators. Think of the Borg from Star Trek: Next Generation and Voyager, not Deep Space Nine actually, Enterprise. Um, so it requires supervision currently. So Microsoft released this thing called Tay, or Taybot. Uh, Again, how many of you have heard of it before? I see a couple of hands raised in the classroom. A couple of people are chuckling because they know exactly what I'm talking about. So Microsoft Tay was this chatbot that Microsoft released on Twitter. And initially, everything went great. You could send a tweet to Tay, and Tay would respond back with something. Well, then the internet did what the internet does best, and they started to mess around with Taybot to see, or mess around with Tay, to see what could happen. And over the course of 16 hours, and think about it for a second, it was out in the wild for 16 hours. Tay ended up turning from a relatively harmless Twitter AI chatbot to something which went full on racist and defending Nazism and anti everything. And it just kind of went down in a flaming, in the old programming, flaming garbage pile. Or flaming garbage pile in, flaming garbage pile out. So it went from Tay went from humans are super cool to full Nazi within less than 24 hours. Um, so like one of the early tweets, can I just say that I'm stoked to meet you? Humans are super cool. To chill everybody or chill, I'm a nice person. I just hate everybody. To I hate feminists and they should all die. And to Hitler was right and I hate the Jews. Um, and it kind of went um, downhill really, really quickly. Microsoft, they kind of were embarrassed with it, rightfully so, and they took her off, or him, her. I don't know if they actually assigned a gender to Tay. They took Tay offline, and they cleaned it up a little bit, and then they accidentally released Tay again, and it kind of all went belly up again. So Tay was one of the examples of a chatbot which was released to the wild that the internet was able to corrupt. And Microsoft actually claimed that there were malicious people that tried to ruin it, which, okay, yeah, some people sent a whole bunch of tweets that ended up ruining Tay. But at the same time, that's an example of you have to maintain supervision over these chatbots. Otherwise, they're going to start to just repeat back what they have learned. And that's really what it was doing is a lot of people would send these offensive tweets to Tay, and then Tay would learn over time what was going on with it and would take some of it, and then whenever somebody tweeted something which it had learned before, suddenly Tay was like, "Oh, I've seen that before. I'm going to go ahead and spout out this." And so, yeah, they require supervision. Other limitations. They're currently very expensive to develop and maintain, and very expensive, not necessarily in the actual software parts, but to run this, it can require a lot of hardware to actually run a or train a artificial intelligence system. It also needs a lot of people paying attention to it and tweaking it and figuring out what is working, what isn't working, how they can change things, and all that sort of stuff. Also, every system is unique and usually it's for only one purpose. So it's not a true general purpose robot that can suddenly, or general purpose artificial intelligence that can understand everything. No, it's generally a system which knows it's one specific thing, and it may be really, really good at its one specific thing, but that's all it really knows. Um, Also, AI doesn't have any creativity. Now, it's not to say that it can't create things, it's it is not able to arbitrarily decide, oh, I'm going to create this painting now, or I'm going to arbitrarily compose a piece of music. You can program it to create a piece of music, but it's not able to create a piece of music from its own ideas uh, or its own drive. It has to be instructed to create music, and some of the music is, yeah, some of it's okay listening to, but some of it is just kind of weird, and to a human, it would sound weird. So those are some of the limitations, and there are many, many other limitations, but that's just a small example of them. So what applications do these have? Well, big one right now, self-driving cars. Tesla is out there. They have some of their self-driving capabilities. They have the Summon feature. I can't remember their official marketing name for it or whatever, but basically, if you have a Tesla and it has this capability built in, which I think all of them do, but you can stand on one end of a parking lot and summon your car to you. And what it will do, it will back out of the spot and then drive or navigate around the parking lot to where you're located. And it's actually kind of cool. Um, it has limitations and it's not perfect, but it is a cool example of the technology. It also has its self-driving, some self-driving. It's let's see, it was called Autopilot. I think they renamed it because they ran into problems with the government on the naming of it, but maybe it's still called Autopilot. I don't remember. But where basically it can drive from point A to point B without real driver interaction. The driver still has to pay attention, keep their hand on the steering wheel and everything, but it can drive and navigate through an interstate and take an exit and that sort of stuff without the driver actually having to do that. They are working on full self-driving cars. Google has been working on full self-driving cars to where it can drive itself everywhere. Uber has as well. Waymo, I think they've been working on it. A lot of companies have been looking on or been researching full self-driving cars, and there's a lot of money in self-driving cars. If you can develop your own system, which is 100% crash-proof and can drive the best out of everything, you can make well, you will be the richest person in the world probably. Speech recognition. Uh, YouTube already does this for a lot of the stuff with closed captioning. It will automatically transcribe what I say and do it as text on the YouTube video. It's not in real time, I believe, but I think it's fairly real time. Um, there are other systems which will do it. So if you talk into your phone, if you say, "Okay, Google" or "Hey Siri," and speaking of which, my phone just turned on because I said that. Um, but if you do that, that's doing speech recognition, and that's using a some sort of neural network on the back end, which is training it, or which has been trained. Like we had already mentioned, game playing, either board games or video games, are one of the big applications for it. Data analysis. So, like I had mentioned, the machine learning for trading. That's a lot of data analysis. Computer vision also uses data analysis and artificial intelligence for it. Then there's these things called expert systems. And I'm going to talk about this very briefly, but what is an expert system? Well, it's an artificial intelligence where it is a computer system that emulates the decision making of a human expert. And so one of the limitations I mentioned is that it's used for a specific purpose. Well, that's an expert system. It is programmed in such a way that it's designed to try to have the same breadth of knowledge that an expert in that field would have. So MySyn is one of the early expert systems that used artificial intelligence to identify bacteria causing severe infections and recommend antibiotics. It was designed to augment what a doctor would do. Now, it's not designed to replace a doctor because a doctor is able to see a lot more information than the specific realm of information that MySyn has, but it was designed to you feed it a whole bunch of information and it will identify what type of bacteria that is and recommend certain antibiotics to a doctor, and then the doctor would go on and determine whether that was proper or not. There's also systems to look at x-rays and CT scans and try to identify various abnormalities in the scan. So expert systems are designed for a specific purpose, but they're designed to be an expert in that specific field. Other applications, planning, robotics. Again, robots is a huge, huge field, almost as big as artificial intelligence, maybe not as big, because robotics takes a lot more physical components, whereas artificial intelligence, you can do a lot of it on a computer and then just offload it to a server in the cloud somewhere. But robotics, it uses a lot of artificial intelligence. And then there's a Cleverbot, which Cleverbot is very similar to Tay, only it's, well, not. So I can say, hi. And it responds back, how are you? I am great. That's good. How are you? And this is a chatbot. Um, well, Cleverbot, which is a chatbot. And what it does is you type in a phrase or a sentence like, what are you doing today? Nothing. And it has a huge table of various responses. And it basically takes your sentence and it breaks it up into sections. So, like, looks at the first word, what? Well, it knows that what is typically a question, especially since there is a question at the end. And so it knows to answer that. It looks at doing to see it as an action. Today, maybe it has some relevance for that. And it breaks it all up and then it just looks through all that and it takes all that, puts it together, and then it spits out an answer. It's not really intelligent because it's not coming up with its own responses. It's just basing off of what it has seen before. And so it's a chatbot, but it is still exhibiting some forms of artificial intelligence just because it learns from what other people have been saying or what other people have talked to it about. So are there other applications? There's applications literally everywhere. Your phone has several applications. My phone, for instance, it's a Pixel. When there's music playing around me, it will actually output the song name and the artist of it. And that has a neural network which can listen to bits of the song and then match up what it's doing. So there's literally endless possibilities for artificial intelligence and machine learning. So I encourage you to go out there and think of what might actually be using artificial intelligence or what artificial intelligence could actually be used for to improve the world around us. So now we've got to get into two key forms of artificial intelligence and machine learning, or specifically learning. So there's supervised learning and then there's unsupervised learning. And we're going to talk about these briefly and see an example of supervised learning. So supervised learning is teaching a system what the answer should be for a set of inputs. So you give it a bunch of inputs along with labels of that input to classify it, and then you train it that way. It's used when you want to train a system to predict answers based off of previous answers. Whereas unsupervised learning is the exact opposite. You give it a whole bunch of data and you let it decide for itself, what does that data mean? What can the system derive from that data? Um, and it's one of those where you want to develop a system that discovers answers that are not readily apparent. So thinking back a little bit, what have I already talked about, which seems like an unsupervised system or an unsupervised learning system? Well, think about AlphaGo. AlphaGo was unsupervised learning. They gave it the rules, but that's not training it on how to act. They just gave it a number of rules and said, have at it. And it played against itself until it won or lost. And then it did it again. And that was unsupervised learning. Whereas checkers, for instance, might have been a supervised system where they gave it a number of states of the board with what it believed was the next state. So let's look at an example of classification and supervised learning. So supervised learning, you give it a whole bunch of data and you give it a label saying what it is. So let's look at this classification example. So the first question is a horse Acerus? Now, in all fairness, I did not come up with this idea myself. I got this from a really good video by Sebastian Thrun. He is actually the creator of Udacity, and he's a pioneer in a lot of artificial intelligence and robotics. And so I kind of adapted it from what he did in one of his first videos. But let's ask a question: is a horse Acerus? And I encourage you to not Google what Acerus means first, just to kind of go through this, and then you'll learn what it is. So if I was a computer system and I wanted to determine if I was given a arbitrary animal, or in this case a horse, could I say if it's Acerus or not? Well, I don't know. So I'm going to train myself whether or not a horse is Acerus. So the first thing I might do is pass in a rhinoceros and a whole bunch of data about a rhinoceros, but pass in a rhinoceros and say, is this Acerus? Well, I have no information to base off of, so I'm going to go ahead and say, yes, it is Acerus. Well, and the survey says it is not Acerus. Okay, well, now I have a little bit of information. So, not Acerus. So I can look at this. It's a rhinoceros. I think it has a four-chambered stomach. It has four legs, skin, has a brain. Who knows what else it might have, but I get these little bits of information from it. So it is not Acerus. So now I have a cow. Oh, I know what a cow is, and I know from the previous one a rhinoceros is Acerus, or is not Acerus. And so I look at this cow and I'm going to say, okay, well, it's a lot of features similar to a rhinoceros, so I'm going to say it's not Acerus. It has four legs, has a four-chambered stomach. It is not Acerus. Sweet. Now, can I say from that whether a horse is Acerus or not Acerus? No, that's not enough information. So we're going to train it a little bit more. So now I go, a little dog, a Shiba Inu, which that's one of my dogs. Well, that's actually not a picture of one of my dogs, but I have a dog like that. But anyway, so Shiba Inu. Well, I know that this is not like a cow. It's not big like a cow. Doesn't have a four-chambered heart. It does have four legs. So maybe that I could say that Acerus or not Acerus is having or not having four legs. Um, but I'm going to say that since it doesn't have a four-chambered heart and the other two did, um, it's not Acerus, or it is Acerus because the other two were not Acerus. I'm going to say that this is Acerus. And hey, yep, I am right. So, okay, we have more information to base off of. Nope, now we have a seal. Well, suddenly now it doesn't have any legs, doesn't have a four-chambered heart. I don't know about this. I could just flip a coin. I'm going to say it is Acerus. And hey, now we are correct. Although we can't use legs as a classification for it because, well, this doesn't have any legs. Um, we could still use the four-chambered stomach as a classification. I'm purposely ignoring the one feature which is common between them just from using it as an example. Okay, so now we look at a narwhal. And well, we already know that a seal is Acerus, and it does not have a four-chambered heart. Shiba Inu is Acerus, does not have four-chambered heart or four-chambered stomach. Um, and so a narwhal, well, is that Acerus or not? Well, so we're going to go ahead and say it's Acerus. Oh, suddenly it's not Acerus. So now we know that the stomach doesn't have anything to do with it. The four legs don't have anything to do with it. So we keep looking through this. We have a Triceratops. Well, this looks kind of like a rhinoceros. I don't know if it has a four-chambered heart or not. I don't remember that from when I was younger, but I'm going to go ahead and say that this is not Acerus, and that is true. And we look at a parrot. Well, it only has 2 feet, but again, we already figured out that 4 legs or number of legs don't really matter. So we are going to say that this is Acerus. And we look at a turtle or sea turtle, and we're going to say that this is also Acerus. We're starting to get an idea of what may or may not be, what Acerus may or may not mean. Now, if we look at this, well, this is a goat. Well, 2 goats, a couple more goats in the background, but we're specifically looking at this goat here. Well, we know that stomach doesn't have anything to do with it. We know that legs don't have anything to do with it. What other feature does have something to do with it? Well, maybe the things on top of the head. So that is not Acerus. A little cat with a bow tie, cute little bow tie, because bow ties are cool. Um, Doctor Who reference. Uh, let's say that this cat is Acerus. Oh, it is Acerus. So now we get on to back to the horse. Is the horse Acerus or not Acerus? And at this point, you have a fairly good idea of what Acerus means. I mean, I kind of gave you a really, really big hint 2 slides ago when I showed you the goat, but we will say that this horse is Acerus, which now it is. And so Acerus is lacking horns or antenna. So a horse is Acerus, a cat is Acerus, but a goat, because this goat has horns, is not Acerus. And so given that, now you can be given any arbitrary image of an animal and asked, is it Acerus or not? And you'll have a fairly good idea of whether or not it is. And you can use that to make a prediction. That's really what classification for a computer system is. Now, is it 100% accurate? No. If I gave you an image of a ant and I said, is this Acerus or not Acerus? And you had no idea that Acerus means lacking antenna and you only knew it about horns, well, now suddenly you would have to make a guess. And that's really what supervised learning does is you give it enough information for it to make an educated guess. And yeah, it's going to be wrong from time to time, but you want to get its accuracy to 85 to 90%, somewhere around there. So if you give it data, it is more accurate than not. So now we look at unsupervised learning examples. So you give it a whole large number of photos that you want to divide into groups of individuals. And let's say you don't know who everybody is in all these photos, but you want the artificial intelligence system or the machine learning system to take all of these photos and classify them based off of who's in each of the photos. And you don't have to tell it who is who, it just can group these photos up automatically. It's kind of like what Facebook does with all these photos that you put up there. It can you put it up there and then it tags it. Um, you can also have it. You give it a whole bunch of molecules and let it determine which are drugs or which molecules combined together make what things, or how to combine certain things, or to determine algorithms on which is which. Or you give it a whole bunch of information such as you want to know if people buy X, will they also buy Y? You don't want to classify it as saying, okay, these people bought this and now they're buying that. You want to just give it a whole bunch of data and then just make a prediction based off of what somebody will do. Or if you want to group data together um, and to a certain grouping of information, so like the stock market information. You have all this information as to what this particular stock does, and you can train it with a supervised learning of at this time you bought, this time you sold, bought, sold, etc. Or you can just train it in an unsupervised by giving it all the data and letting it determine for itself whether it should buy or sell automatically. There's also this genetic car. This is a pretty cool site. Let's see. So what this is a car which is automatically generated, and it generates 20 cars, and it sends it along this path. Um, and then it chooses the best car, which in this case happens to be car number 17, and it keeps going until it actually gets stuck, which this one's going a lot. There we go. It finally got stuck. And now it generates 20 new cars, but it takes a little bit from car number 17 to determine what features the car should have. So in this case, it has two wheels. One is bigger than the other. It has kind of this shape like that. Has one wheel in the front, one wheel in the back, and it just keeps doing this. And this is using the genetic algorithm to determine which form is best. And it's really using machine learning to determine um, what is the best performing attribute. So this is an example of unsupervised learning because you aren't actually saying what features are best. And if you refresh this, uh, it's going to choose 20 new, completely different random ones and then just build it off of that. So you can see that some of them aren't really getting that far. That one's getting a little bit further. And then it gets stuck. So it doesn't go nearly as far. So this is an example of unsupervised learning. Go ahead and close out of that. And then this YouTube video, I highly, highly, highly encourage you to watch it. It's only 14 minutes long. It's this guy by the name of Matt Smith. He's a English mathematician that he has his own stand-up math comedy routine and everything. But uh, they created this system called Menace. And Menace was basically teaching a teaching a physical system to play tic-tac-toe. And they did that by creating a bunch of matchboxes with colored pieces in there and training it to play tic-tac-toe and win. And so I encourage you to watch that video. We aren't going to watch it. It's about 15 minutes long, but watch that video, and it's rather interesting. At least I found it interesting. So now we move on to computer vision. And what is computer vision? It's a field that deals with how computers can be made to understand digital images and videos. Computers use neural networks to analyze and process images to determine what components exist and what the image tries to portray. Um, Now, I am actually in the computer vision class through my master's program, and it's a really fascinating field. Um, Speaking of which, I think I have my final in a couple of hours that I can take. But it's when you think of computer vision, you try to think of how can computers see the world around them? How can they figure out what to do? And it's one of those things that until you actually start doing it, it's really hard to understand what it's trying to do or why something is trying to work in a certain way. And Thursday, I'll show you a couple of examples of things that I had created. But some of it is if you have two photos, how do you match up those photos? How do you, like on your phone, you can take a panorama, which is basically you stand at one point, you take a picture, you rotate around, you end it, and it stitches all pictures together to make one big wide photo. How does a computer actually do that? How does it create that panorama? And well, the magic behind it is all in math. As long as you understand linear algebra, computer vision isn't that difficult. Well, okay, it's difficult, but it's a lot easier if you understand linear algebra. And there's a lot of math behind it. It's and some of the math is really really interesting. But it can take these images and it just loads these images up into a huge matrix of pixel values, and then you figure out what to do. And so, like one of the projects that I had to do was they gave me a video of a brick wall, and that brick wall had 4 points on it. And the camera moved around and everything, but all that was on the brick wall was 4 points. And I had to write a program which would identify those 4 points and then put my own image in there. So as they move the camera around, my image would warp and change and shift around following those 4 points. It was actually really, it was a lot of fun. So computer vision is it's a huge, huge field, and a lot of people spend a lot of time and money in it to try to get computers to see the world around them and see what is actually out there. It's the same thing as when you take a picture and upload it to Facebook, or even on your camera, on your phone, when you take a picture and it's able to detect people in there, that's using computer vision. Um, and the cameras nowadays, which are able to detect when somebody is sneezing or somebody's blinking and take a couple of pictures and then choose the picture where they are not doing that. That's all using computer vision. It's also using neural networks to analyze it. So they train a system based off of thousands and thousands of pictures of people, and maybe they take these pictures of people sneezing and people not sneezing, and they train using classification who is sneezing and who is not sneezing, and then they build the system, and then they just load that on your phone, and then your phone doesn't have to figure out who is sneezing or who's not sneezing. It takes a picture, it runs it through the system, and it can be really quick to actually test it, but it runs it through the system and then outputs a result. And so computer vision is actually fascinating. And before I took this class, I knew that computer vision was interesting, but now that I've spent the last 4 months actually working with computer vision, it's a really, really fascinating and really, really complex and big field. And so I encourage you to look more, and I will show you examples next Thursday of a couple of things. But um, images or Google image search is a real big computer vision system to where you can either do a search for something like Go, um, and it will find that there. This happens to be Go programming language, or you can take a image. Let's go ahead and choose this image. Uh, do, 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 do. Oh, that's okay. Let's go ahead and copy image address. Copy image address, and you can do a search for. You can paste an image URL here. Search by image. See if this actually works. Since I tested, there we go. And so it searches for that, and possible related search, word go. Um, and it has examples there. Oh, come to find out, it actually found that one. May not be the exact one, has other examples. But this does a reverse image search where it detected what type of image that was and what was in there, in this case, the word go, and then it did a search based off of that. So Google Image Search is a huge computer vision project, and it's one of those fascinating things on how they actually managed to get it to work and recognize it. The last thing I'm going to talk about today, just because it may or may not be on your test on Thursday, is neural networks. So, what is a neural network? So I mentioned it in the last slide that computer vision uses neural networks, but what is a neural network? So it is a system which is modeled after your brain and how your brain works. So typically with the neural network, you have an input layer, and then you'll have several hidden layers, which I'm kind of glossing over the hidden layers for the moment. Um, but then you'll have an output layer, and that determines what the answer should be. So um, your input layers take your input, processes it through your hidden layers, um, depending on what type of network you have, and then it passes the answer out to the output layer. So for like image recognition, you would break the image up into individual sections and then process each section, and then you would create an output saying what type of image that is. Or you might create an output saying that in the case of, well, one thing that I just my final project was I took in a bunch of activities. So like somebody walking or somebody running or somebody clapping their hands together. I would take that. I didn't actually use a neural network for this, but you can. You take that the videos, You pass it into the neural network. It automatically splices it up, slices, dices, um, using Ginsu knives and all the sort of that. No. It takes all of those images and videos and figures out what type of action is going on in there, and then it passes to the output. Maybe in this case, we wanted to recognize six different actions, like boxing, and actually, I did have to recognize six different actions, but boxing, hand waving, hand clapping, running, jogging, or walking. And so your input would be the video or the images. Your hidden layers will do all the calculations and bouncing around between the neurons and everything, much like your brain. And then the output will be a number. And the number might be a 1 or 100% that it is hand clapping. Or it might be it's 95% confident that it's hand clapping and it is 5% confident that they are walking in the video or some combination thereof. And so it just basically uses statistics and then you take that output to determine what you want to do with it. So it basically goes from your input to your hidden layer, and typically to the first hidden layer. You might have multiple hidden layers. And if you have multiple hidden layers, it goes to the first hidden layer, then it gets bounced to the next one. And so the first hidden layer might recognize um, big sections of the image. And then the second hidden layer might recognize small sections of those bigger sections. And the next hidden layer might recognize specific color channels or specific things in those images. And so each hidden layer can do something different. Um, but eventually it gets to the end and it gets passed out to the output layer, and that lights up certain nodes saying what it is. Now, there's other forms of neural networks called recurrent neural networks, where basically it goes through this process and then before going to the output layer, it goes back around. It goes back to the first hidden layer, and it goes processing again. And it keeps doing that multiple times. It may change some numbers every time it iterates through that until it finally reaches a certain threshold that then it exits out and kicks out an answer. There's also convolutional neural networks, and that's used for image recognition. There's all sorts of different neural networks, and I'm blanking on a lot of them, which I wish I had a list in front of me, but maybe next time. But the neural networks, it's literally how the brain works, and then it just does all the processing and kicks it out there. So these two YouTube videos, one of those is on I believe it's on a neural network. I have this up on my other screen. It's not actually, let me click on it. See, so the first YouTube video is, it's a video from Three Blue, One Brown. They make videos on YouTube. And it's actually about deep learning, and it's actually a really, really good video. I encourage you to watch that. It's a bit longer, I think. I think it's 20 minutes. And then the second video is it's another really good video. It's only 5 minutes long. Well, 6 minutes. This guy created a system called Mario, and what he did, it took a level in Mario. I think it was Super Mario Brothers. Super Mario World. And what he did is he trained a neural network based off of Super Mario World. He didn't give it any training or anything. He just basically said, okay, get to the end of this. And the system would figure out which path it should actually take, when it should press which buttons, how it should do stuff. And so it's a 6 minute long video, but I encourage you to watch that. Once you watch it, you'll go, wow, that's really, really cool. And if you're anything like me, which I hope that you are just like me because, well, yep, that'd be cool. But if you're anything like me, that will make want to explore um, the neural networks and artificial intelligence even more. So I'm going to go ahead and end here for today. Um, Thursday, we're going to talk about recognition problems. I'm going to show you some examples of things that I have worked on. We're also going to talk about ethics in AI and various ethical questions and see things like that. I will have the test available for you Thursday. I still have to add it to D2L, but I will do that. I haven't seen any questions pop up in the chat, so either you have already fallen asleep and are snoring on the keyboard, or maybe you don't have any questions. But either way, um, I hope you all have a great Tuesday, great Wednesday, and I will see you all on Thursday. Thank you.